Last time, we had realized that we should not think about the speed of light as a material object, but rather we should think about it as a rule that describes the relationship between space and time. Now, experimentally, since it has been discovered that the speed of light is invariant, we realize that we shouldn't try to model our universe as 3D space, as that would only work if velocities are relative. So instead, we need to determine a new way to construct a representation of reality by perhaps modeling it as a set of events. In doing so, we could imagine a new space that encodes our three spatial dimensions as well as our one dimension of time. In doing so, we can construct something known as 4D space-time. And we can think about this as a rubber sheet that we will call our base space. In this new representation of reality, I could imagine myself just sitting here on a chair as being denoted by this singular point. It encodes all three of my spatial dimensions as well as where I am in time. And if I choose to not physically move, it turns out I would still be mapping out a path on our 4D space-time as I'm still moving in the time direction to the right, even though I haven't moved at all in my spatial direction. Now, when we do so, we might realize that we need a construction to measure this idea of distance. Now, historically, we may have used the Pythagorean theorem to measure our distance squared as being variations in our spatial directions, but it turns out we cannot actually use the Pythagorean theorem in this case because we're not measuring distance. We have this concept of time that is encoded as well. So instead, we can use a modified version of the Pythagorean theorem known as the Minkowski metric. And this is very similar, except instead of distance, we have this idea of our space-time interval, which we will denote S. And we still have our spatial directions that are all squared, but we also have an added time dimension that is squared. And we will denote our time with a negative sign to highlight that it is different from the spatial directions. And we can think of this like a ruler. Now, what we realize is at each point in the base space, we can imagine an entire plane tangential to that point. And tangent to this base space, we might give this a name, we call this our tangent space, and we can imagine arrows or vectors ranging in an infinitely circular path at our point, where this would encode all of the potential directions that we can move on our base space. Now, it turns out we know intuitively that some directions are just not possible. Namely, we cannot move backward in time. That is not allowed. Experimentally, we have also discovered that it's not possible for us to have a velocity that is greater than the speed of light. So we see that there are some restrictions on our possible allowed motions. And one way to identify what is actually allowed is by placing this Minkowski metric, something that we can think of as our space-time ruler, at this particular point. And When we do so, we could imagine not moving from a particular point. That is, having a space-time interval of 0. Now, for the sake of clarity, I'll just limit this to 2 dimensions. So we'll have 1 dimension of space and 1 dimension of time. If we plug in this space-time interval of 0 into our equation with just 2 dimensions, we have 0 is equal to x squared minus t squared, and this allows us to rewrite x is equal to plus or minus t, or 1t. This traces out a boundary on our tangent space. If you plot this, turns out it maps out something that looks like an X. And we call this boundary the light cone. And it turns out all of the directions that are possible to move are enclosed within this boundary. And only light moves along its boundary where the space-time interval is 0. To take this one step further, if you've ever studied special relativity or watched some of the other videos that exist on YouTube, you will undoubtedly have heard mention of something called a Lorentz transformation. To quickly provide some intuition as to what the Lorentz transformation is describing, it is merely a way of relating 2 different observers viewing the same event in space-time. More specifically, it is a mapping of one observer's vectors in the tangent space to another. The way to think about this is you could imagine that you are perhaps at a skate park just standing still observing what's going on, and a skater could come and pass you by. I'll denote this in green. Now, roughly, we could imagine this as overlapping 2 points in space-time, even though not quite occupying exactly the same space. Now, from this perspective, even though both may be considered at the same point in space-time, both observers will have very different perspectives on what they view to be straight ahead in time. So if we imagine the tangent space, for an observer that is just standing still, they're restricted by the light cone, and they might just not be moving. From the perspective of the skater's tangent space, they are also restricted by the light cone. They both agree on what is possible and impossible, but the skater might have a velocity that is pointing in a particular direction. The Lorentz transformation is merely a mapping of one observer's point of view in the tangent space to another. Now, to summarize, we have constructed a new representation of reality, modeling it as a set of events that occur on a 4D space-time base space. And we found that if you zoom in at a point, you can imagine a tangent space of possible directions. And there is a light cone defined on the tangent space that can be viewed as a rule book describing what motions are possible along the base space. Furthermore, we have also discovered that the Lorentz transformation can be viewed as a type of rotation of this light cone to view different observers' perspectives. Now, we have uncovered something truly deep here. We have discovered that light actually determines the shape of our universe. And more deeply, we've actually touched upon the heart of mathematics and physics, as we have discovered that symmetry determines geometry.